Now let's discuss the reactions of esters. So we can have a generic ester. Remember that has an OR group attached to the carbonyl. Or we could have a specific one where we identify the R group. And let's do a methyl ester in this case. So there's a methyl group here. We call it a methyl ester. The name of this compound is methyl acetate. And an ester can be reacted with water and acid. And that's a catalyst, so we don't add a whole ton of acid, we just add a few drops. And we can revert the ester back to the carboxylic acid. So the carboxylic acid plus the alcohol. And so this reaction is reversible, and depending on the conditions, we can favor the products or the reactants. And so I should point out that the left-facing reaction, the one that produces ester from alcohol and carboxylic acid using catalytic H2SO4. Let's say H2SO4, I'll abbreviate catalyst with CAT, and that produces methyl acetate and water. That is called Fischer esterification, named after a scientist named Fischer who developed this reaction or studied it a long time ago. So that's a very common way of making esters. Fischer esterification requires a carboxylic acid, some alcohol, doesn't have to be methanol, as long as it has an alcohol group that's reasonably accessible, and a little bit of acid catalyst. We can heat that up and produce ester and water. And in this reaction up here, the one I showed that was reversible, which basically was the hydrolysis of an ester going to the right, and so let's draw that here. We'll call that hydrolysis. Hydrolysis means breaking bonds using water. Or if we go to the left, that's called Fischer esterification. So I'm just going to abbreviate that FE, but it's Fischer esterification going to the left. We can favor either hydrolysis or esterification by judicial use of certain laboratory equipment. Mainly it's going to be our ability to keep water away from our ester. If we want to produce an ester, we don't want any water around to react with it. And so we want to use equipment that removes water. And so we remove water when we make esters. So in Fischer esterification, we use equipment that can keep the water that's produced away from the ester so that it doesn't react with the ester and undergo hydrolysis. When we desire hydrolysis, we simply just add a lot of water, cook our ester with some acid, and we might drive off the methanol here to use Le Chatelier's principle to force the reaction to the right. So we can use Le Chatelier's principle either by removing water to force the reaction left, or removing the alcohol to force the reaction right. We could also use an acid chloride to produce esters. We don't see too much of this in biology, of course, because acid chlorides are really much too reactive to be found in nature. They're more of a chemical that's produced in the lab and then used in further synthesis. So here, we mix that acid chloride with the alcohol, and as you've seen in previous videos, we end up with an ester. We also get HCl, and so I used pyridine, which is a base, to soak up that strong acid, because most of the time we don't want any strong acid present. And so here's pyridine, and so what we get is that base being a nice sponge for the HCl that's produced. And so the base will react with the proton to form pyridinium, and then we have the chloride anion in close proximity. And so we can use an acid chloride, of course, to make this less reactive carboxylic acid derivative, the ester. And lastly, I'd like to discuss saponification of esters. So that's a reaction of ester. And so we can take our generic ester. Saponification is when we react our ester with this strong base and strong nucleophile, sodium hydroxide. And what we end up with is the sodium salt of the carboxylic acid, and we end up with HOR, or ROH, the alcohol that's part of the ester to begin with. And typically the second step in saponification is work up with H3O+, and we end up with a protonated carboxylic acid. So that's called saponification. It's simply degrading the ester in a different manner to get a carboxylic acid. And we can relate this to biology. A lipid, or a triglyceride more specifically, is a triester. I'm not going to draw these fatty acid chains in all their glory. I'm just going to represent them with squiggly lines. But a triglyceride essentially has a glycerol backbone, which is right here, and it has 3 fatty acids with their long chains of hydrocarbons and their acid end group, and we have 3 ester bonds. So if we react this triglyceride with 3 equivalents of sodium hydroxide, we end up with glycerol. This is the alcohol portion of the ester, and we get 3 times carboxylates. I'm not going to draw that, but this is a minus, and there's a sodium here. And before we had modern chemistry, this made a good soap. Let's say we'll call it a good soap. This is polar. The polar head group can dissolve in water. And the nonpolar tail of this fatty acid carboxylate can dissolve grease into the water, can actually remove the grease from our clothes or our hands. So we'll call it dissolves grease. And so we can use this soap molecule. It has a polar end and a nonpolar end to clean up our bodies or our clothes. And modern soaps have operated under the same principle. They're a little more complex, though, than simply this fatty acid carboxylate. Let's look a little closer at the mechanism for the saponification of an ester using hydroxide to produce a carboxylate. And let's use the sodium cation. We'll just take that along. It really doesn't play a role in the reaction, but it does help us with the counter ion for each of these negative ions. So again, the carbonyl is polarized such that it can accept a lone pair of electrons from a nucleophile, and we can form this tetrahedral intermediate. And here's our new CO bond from the OH. Everything still has 1 negative charge from the original OH, except now that negative charge is on the O. The next step is to eliminate the leaving group. In this case, it's going to be the OR minus. And that's going to give us essentially a carboxylic acid. And this strong base. It's important to keep that in mind. We've just made a very strong base, and we have a carboxylic acid. And those are reasonable acids. And so the immediate step is going to be deprotonation of the OH on the acid to form the carboxylate anion plus HOR, or the new alcohol. So we have a proton transfer step here, PT. And that gets us to the carboxylate. We can draw in the sodium if it makes us feel better. That came along with the sodium hydroxide. Now it's a counter ion to the carboxylate, and we have our newly formed alcohol. And so this is saponification. Let's look a little closer at the mechanism for ester formation using an alcohol and an acid chloride. So we know that carboxylic acid derivatives are polarized, and they have polar bonds, both the CO bond and the CL bond, CCl bond, are polar, and so that implies that they should be able to accept electrons from a nucleophile. And indeed, the first step is nucleophilic attack on the carbonyl carbon, like we've seen in other mechanisms. And that gives us to this intermediate. There's now a negative charge on the O. We still have the chlorine. We have the new CO bond, the ethyl group, and the original hydrogen. Positive charge on the O, given that it has 3 bonds and a lone pair. And so now we can do one of two things. We can either lose the leaving group or do the proton transfer. Most likely the proton transfer happens first, so let's do that. We use pyridine. That's the base that we often use when we react acid chlorides. And so that will be a proton transfer, which will result in the proton being transferred to the pyridine, and so we get a pyridinium cation. Now our oxygen has 2 lone pairs, no charge, and we have the pyridinium cation, which is up there, so I won't redraw it. The last step then is to eject the leaving group by reforming the CO double bond and losing chloride, and that brings us directly to this ester. We form the chloride. So that's the mechanism for nucleophilic attack on a carboxylic acid chloride.